Acid-base behavior and strength. When you are working with non-aqueous solvents, what you consider an acid or a base in water not always applies. The values of acidity constants, of basicity constants that you find in tables refer to the ionization of that particular acid or that particular that particular base in water. When you are working in a non-aqueous solvent, when you are not working in water, things can look very differently. For example, hydrochloric acid is a strong acid. In water, compared to water, it will behave as a strong acid. However, hydrochloric acid is a weak acid when dissolved in acetic acid, which is itself an acid. We call that a leveling effect. That is called a leveling effect. If you have a solvent which is a good proton acceptor, for example, ammonia, i.e. a solvent that has a basic character that will behave as a base, that will encourage acids to ionize further. In a basic solvent, all acids are strong, all of them, because the solvent encourages that acid behavior, that donating of hydrogen ions, because the solvent itself is a good proton acceptor. And we call that the leveling effect. We say that solvent has a leveling effect on that acid. In an acidic solvent, for example, if you're using sulfuric acid or acetic acid or fluorhydric acid, is the other way around. Then because those solvents are good proton donors, that will help bases ionize. So while bases will be stronger in an acidic solvent, acids will be weak under those conditions. So if you're using as an acidic solvent, then yes, the ionization of a base, if you're trying to dissolve a base, the ionization will be facilitated, so the base will be a stronger base. When you dissolve an acid, the ionization of the acid will be curtailed. So most acids will be weak in those conditions, and some of them will even ionize as if they were bases, because they might be acids in water as a solvent, but that doesn't mean that they behave as a base in another solvent, when that solvent is more acidic than what they are, has more tendency to donate protons than they are. That can bring you quite an interesting and sometimes very dramatic effects. For example, perchloric acid is one of the typical strong acids. However, when you dissolve perchloric acid in sulfuric acid, when you're using sulfuric acid as a solvent, it behaves as a weak acid, and is a very, very weak acid. It's practically non-ionized. So because acid and base is a relative term, depending on what those acids or bases are confronted to, they will adapt their behavior. So perchloric acid is a strong acid in water. However, when faced with another strong acid as a solvent, that will weaken that tendency to donate hydrogen ions. The effect is even more dramatic with nitric acid, again, which is a strong acid, although not as strong as perchloric. In sulfuric acid, nitric acid ionizes as a base, donating hydroxyl ions. Look at here, this is nitric acid, and look at the ions it's forming. And this, by the way, reaction, we have looked at it because it's in electrophilic aromatic substitutions, is what the reaction we use to introduce nitro groups in an aromatic compound. So when we are looking at non-aqueous solvents, just because a compound is called acid That doesn't mean that it will be an acid in that particular solvent. The word acid is applied because in water they will be acids, but they might not be acids when you are using a different solvent. And here, for example, the example of sulfuric acid. The Bronsted-Lowry definition of what an acid is or what a base is can be adapted to solvents other than water. So if you're in water or in a protic solvent, then you talk about an acid donates hydrogen ions, a base accepts hydrogen ions. When you're looking at a solvent that self-ionizes, but in which the hydrogen ions does not really make sense, you can define an acid as the substance that will produce the cation characteristic of the solvent, and a base, a substance that produces the anion, which is characteristic of the solvent. So instead of talking about hydrogen ions and accepting them and donating them, you look at the cation characteristic of the solvent or the anion characteristic of the solvent, and that will tell you whether they behave as an acid or as a base. So looking at this slightly different rewording of the Bronsted-Lowry definition, a solver-oriented definition, if we look at the self-ionization of water, which is a traditional reaction that we all know, we have that a substances that produces the cation of the process will be an acid, and a substance that produces the anion of water will be a base. This is the self-ionization of dinitrogen tetroxide. So as you can see, you don't need to have hydrogen ions or any hydrogen for that matter. You just need a solvent or a compound that self-ionizes. So a compound in dinitrogen tetroxide that adds to the nitrogen monoxide cation will be an acid. And a substance that in dissolving dinitrogen tetroxide adds to the nitrate, the concentration of nitrates in the solution will be a base. So I'm going to ask you to stop the video for a couple of minutes, do the self-ionization reaction of ammonia, and answer the question: does ammonium chloride in ammonia behave as an acid or as a base? Stop the video now, please. I hope you stopped the video and had a go at the exercises. So the first step is the self-ionization reaction of ammonia. So the two ions that you release are the ammonium ion and the amide anion. And then we look at ammonium chloride. When ammonium chloride dissociates, it will dissociate in the two ions, the ammonium ion and the chloride anion. So because ammonium chloride adds to the positive ion of the self-ionization, the reaction of ammonia, it would behave as an acid. So ammonium chloride would be an acid in dissolving ammonia. So again, you don't need to look at hydrogen ions or hydroxyl ions. You look at the positive ion and the negative ion of that self-ionization reaction. And then you decide whether that particular compound dissolving that solvent that self-ionizes is an acid or a base. This is just a table of various typical non-aqueous solvents, and some of them are protics and some of them are aprotics, and the range in which they are a liquid, which is another thing that you need to take into account when using a particular solvent. And as you can see, it varies. Some of them have a very, very specific range. All others, like for example sulfuric acid, have quite a large range, although we will see that sulfuric acid has some difficulties to be used as a solvent, one of them being that it's very viscous. So this again is just a way of that you can decide for a particular reaction, for a particular temperature, what is one of the conditions you will need to check is that that particular solvent is actually liquid in the temperature range you want to use it.